Now let's look at the case where we have 0 as an eigenvalue. Say lambda 1 is 0. Lambda 2 can be anything else. In this case, consider lambda 2 is positive. It should be similar if we have lambda 2 is negative. So in this case, a general solution, we have two eigenvalues that are distinct. For sure, the matrix is diagonalizable. For sure, we have two independent eigenvectors, like v1 and v2. v1 corresponds to lambda 1, v2 corresponds to lambda 2. Solution c1 v1 e lambda 1 t, c2 v2 e lambda 2 t. Lambda 1 is 0, so xt is c1 v1 plus the rest. This is because lambda 1 is 0, this term is 1. Now look at this solution. We know that it is parallel to v2 for sure. One way you can see that is as xt parallel to v2. You compute the derivative of x prime t. This one c1 v1 just numbers, vectors to scalar there. This first term disappear, 0. Second term, this one prime, c2 v2 lambda 2 e lambda 2 t. So the derivative parallel to v2, so the vector field, the direction vectors always parallel to v2. Okay, that's one way you can see that. So anyway, it is parallel to v2, our solution. Second thing is that now let's look at t tend to infinity. What happened? Solution is this one. When t is equal to plus infinity, t tend to plus infinity, it's go off infinity. E exponential lambda 2t, lambda 2 bigger than 0. This one go to infinity. Exponential lambda 2t. So xt go up infinities. Those. That's the second thing we know. The last thing we know is what about t tend to minus infinity? When we have e lambda 2t, when t is tend to minus infinity, this one tends to 0. The second term tend to 0. The whole thing tend to 0 plus these vectors. xt tend to c1 v1. xt is tend to c1 v1. So depending on the value of v1 or c1, depending on the value of c1, say v1 is this vector, c1 is just a number, a scalar. c1 times v1 may be 2 times v1, 1.5 times v1, just 1 point on the line where you have v1. Yeah. So that's gives us all the data we need to visualize the general picture. Now x1, x2, v1, v2. Assume that here I have v1 like that. It gives us this line. Say v1 here correspond to lambda 1 is 0. v2, the other line, correspond to this line. Correspond to lambda 2 positive. So along this line is go of infinity. The one with exponential lambda 2 t. So that's the first thing. Second thing is that everything else will be parallel for any C2 here. You see, it's only parallel to V2. So parallel to V2. For example, this one parallel to V2. And when that one go to infinity, you see that is go up infinity. X go up infinity when t go to infinity. Go to infinity when xt go to infinity. That's why it looks like that. When t is minus infinity, it's approach a point on this line. The lines correspond to V1. So approach this line. So that's why you see that it just go like this. When it's negative infinity, it just a point leaving here and then start going up infinity. The other side is similar. So this is a picture when we see there is a lambda is 0. So when there is 0 as an eigenvalues, we see parallel lines. Nice. Parallel to the one with lambda non-zero. Origin here. This one corresponds to one solution. This one corresponds to the other solution. Own solution, like parallel to the green one. Now that is the first case. You do the same thing for lambda 2 is negative. Instead of going outward, it's going into this line. So that's the only different thing. What else? What if we have two zeros? So the next case is both lambda are 0. Let's say case 3. Case 1 is positive and 0. Case 2 is negative and 0. Case 3 is 0, 0. Lambda 1 equal to lambda 2 equal to 0. In this case, it gives us two different possibilities. The first one is if we have enough two linearly independent eigenvectors. The second case, we have defective lambda. So defective lambda, this means we missed one eigenvectors. We have one actual and missing one independent eigenvectors. So in this case, geometric multiplicity of 0 is 1. We need to find the generalized eigenvectors. Let's look at the first one first. The first case, 0 is an eigenvalue. Algebraic multiplicity 2. The geometric multiplicity is also 2. In this case, matrix A is diagonalizable, similar to the 0 matrix. The diagonal matrix is 0, 0, 0. So that's why you have something times this is a matrix 0 times something inverse, right? So A is always 0 in this first case. The first case we have two independent eigenvectors. A, the case 3.1. Matrix A has to be the 0 matrix. Nothing to do here because the equation x prime equal to ax is actually 0, 0, 0, 0 x. It is just 0, 0. So x t is just constant. The vectors a constant function c1, c2. So the solution is just one point on the whole plane. So if you want to draw the plane x1, x2 solution is just one point living there. We see here c1, c2 depending on where c1, c2 are just one point. K 3.2. We have defective lambda with one actual eigenvectors. So yeah, what we do is that we try to get first generalized eigenvectors. So we choose it so that it is independent from the actual eigenvectors V, the one we found where we have only one eigenvectors, one linearly independent eigenvectors from V. The actual eigenvectors we found. Second one is we build back the actual one V1. A minus lambda I, lambda is 0, so A minus 0I, which is A times V2, the actual eigenvectors. This gives us the general solution is xt, the first eigenfunction c1 v1 e lambda 1t, lambda 1t is 0t, so 0t is just 1 here, plus the generalized one c2 v1t plus v2 e lambda 2t 0t, so this one is 1. This is the general solution. Look at that, we see that it's head to parallel to v1. There's only one stick with t, it's depend on t here, it's parallel to v1. xt parallel to v1. One way you see that, you do the derivative, both sides, the x prime gives the direction field equal to 0 here, because it's disappear. Derivative in term with respect to t equal to c2 v1. So that's why it's parallel to v1. The direction fields always parallel to v1. Solution curve parallel to v1. What is the other thing? Let's just draw the plane first. x1, x2, v1, assume that's v1, the actual eigenvectors give us this actual line, v1, lambda 1 is 0, v2, assume that we have this v2, give us the other line, this is a generalized one. So now we have when t, this one is c2 times v1 times t plus something, okay, parallel to v1 plus something when now look at this line, the eigenlines, the one correspond to C2 V1t. C2 V1t is go to infinity when t is go to infinity. So V1, assume that I have V1 is like this. When t is go to infinity, C2 V1t is also go to infinity. So say assume that C2 is positive, then it's same direction as our V1. If C2 is negative, then this is negative times V1. It's going to be opposite. Same direction. As V1, opposite direction as from V1. So then the whole term here disappear. It's only xt equals C1 V1. Solution equal to C1 V1. So it's just a point on this line, maybe it's this point. And how to check which direction, which half going up, which half going down, which one is the same, which one is opposite. It depends on the matrix. Assume that we have matrix A like 2 minus 1, 4 minus 2. This one has repeated eigenvalues 0. So lambda 1 equal to lambda 2 equal to 0. And V1, say what is V1? V1 is 2 minus 1. And V2, this is the actual eigenvectors. The generalized one. Eigenvectors is V2 1 0. Now let's draw the picture for this case. So this one V2 1 0. V2 1 0. So V1 2 minus 1, V2 1 0. To check the direction, one lane is the same direction as V1, the other lane is opposite direction as V1. On V1, it just point on V1. Each point on V1 corresponds to one solution curve when we have the case where C2 is 0 here. Each solution curve is on this point actually just one point, fixed point on the curve. In the other two sides, one side is a line parallel, same direction with V1. The other side opposite direction with V1. Now check the direction by checking the direction of one point on this one half plane. Say that we want to check at the point 1 0. Matrix is 2 minus 1, 4 minus 2. Then this point give us 2 minus 1. So 2 minus 1 is this vector pointing down. On this side is the pointing down. Parallel to the red one, going down. Solution curve corresponds to this line. Same for the, let's say, few other. The other side, parallel lines opposite direction. Yeah, so that is all the case we have 0 as an eigenvalues.